negative bond order means Na is greater than Nb. If the bond order is 0 means Nb equals to Na. Okay. In this way, we describe the characteristics of electrons, and we also know bond order equals to bonding electrons by minus anti-bonding electrons by 2. This is the bond order. And next, bond nature. The integral bond order value of 1, 2, 3 correspond to the bond nature of molecule. Means the integral bond order value of 1, 2, 3 correspond to the single, double, triple bond. And magnetic nature. Okay. Magnetic nature. Magnetic nature of two types: paramagnetism, diamagnetism. Paramagnetism. Molecules with one or more unpaired electrons are attracted to a magnetic field. The more unpaired electrons in the molecule is the stronger the attraction. This type of behavior is called paramagnetism. And diamagnetism. Substances with no paired electrons are weakly repelled by magnetic field. This type of molecules are designated as diamagnetism. In general, paramagnetism means it indicates the lone pair of electrons, and diamagnetism means the molecular orbitals in molecule are completely filled without lone pairs. It indicates the diamagnetic nature of molecule. Okay, let me see some example for doing bond order for elements. Here it is the electronic configuration of heavier elements, and it is the electronic configuration of lighter elements. Let me do bond order for hydrogen. What is the atomic number of hydrogen? Yes, the atomic number of hydrogen is 1. Then how many molecules does oxygen molecule possess? Yes, the hydrogen molecule possesses 2 electrons. Then it is the electronic configuration of lighter element. Hydrogen is also a lighter element. So, the electrons are entered into molecular orbitals. For example, hydrogen has only 2 electrons. So, the 2 electrons occupying sigma bonding molecular orbitals means sigma 1 is 2. In hydrogen, there are no anti-bonding electrons, and there are only 2 bonding electrons in hydrogen. We already know bond order equals to bonding electrons minus anti-bonding electrons by 2. So, here 2 bonding molecular orbitals, and there are no anti-bonding electrons in hydrogen. So, bond order equals to 2 minus 0 by 2 equals to 2 by 2, 1. The bond order value of hydrogen is 1. The bond nature of the integral bond order value of 1 correspond to the single bond nature of hydrogen, and there are more bonding electrons in hydrogen than anti-bonding electrons. So, it indicates the stability nature of molecule. Means here there are no lone pair of electrons we seen in hydrogen molecules. So, it indicates the diamagnetic nature of molecule. Here hydrogen is a stable molecule. The bond order value of hydrogen is 1. So, it is correspond to the single bond nature of a hydrogen, and there are no lone pair of electrons in a hydrogen molecule, indicates the diamagnetic nature of hydrogen. In this way, we are able to know some important characteristics of elements. And we do let us do bond order for nitrogen. What is the atomic number of nitrogen? Yes, the atomic number of nitrogen is 7. Then how many electrons does oxygen molecule possess? Yes, it possesses 14 electrons, and it is also a lighter element. So, let us arrange these electrons in a electronic configuration of molecules for lighter elements. Here sigma 1 is 2, sigma asterisk 1 is 2, less than sigma 2 is 2, sigma asterisk 2 is 2, pi 2p x2, pi 2p y2, sigma 2p z2. Okay, let us count how many electrons are present. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 electrons are present in nitrogen molecular orbital. And let us we count how many electrons are entered into the bonding molecular orbital. Okay, let us we see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are entering into bonding molecular orbital. Then how many electrons enter into anti-bonding molecular orbital? Let us we count. 1, 2, 3, 4. 4 electrons enter into anti-bonding molecular orbital. Here asterisk indicates the anti-bonding electrons. Means there are 10 bonding electrons for nitrogen and 4 anti-bonding electrons for nitrogen. As we already know, bond order equals to bonding electrons minus anti-bonding electrons by 2, means 6 by 2 equals to 3. The bond order value of nitrogen is 3 and the integral bond order value of 3 correspond to the triple bond nature of nitrogen. Here bonding electrons are more than anti-bonding electrons. It indicates the molecule is stable. And here we doesn't seen any lone pair of electrons in molecular orbitals of nitrogen. Then it indicates the diamagnetic nature of molecule. So nitrogen is a stable molecule because number of bonding electrons are more than number of anti-bonding electrons, and the bond order value of nitrogen is 3. The integral bond order value of nitrogen correspond to the triple bond nature of molecule, and it is a diamagnetic in nature. And let me do bond order for oxygen. Oxygen is a heavier element. How many electrons does oxygen possess? The atomic number of oxygen is 8. Then oxygen molecule possesses 16 electrons. Let me arrange these electrons in molecular orbitals of molecule for lighter elements. Here sigma 1s2 less than sigma asterisk 1s2 less than sigma 2s2 less than sigma asterisk 2s2. Sigma 2pz2 less than pi 2px2 equals to pi 2py2 less than pi asterisk 2px1 pi asterisk 2py1. Let us we count how many electrons are present in molecular orbitals of oxygen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 electrons are present in molecular orbitals of oxygen molecule. Here let us we count how many electrons can enter into bonding molecular orbital. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are enter into bonding molecular orbital. Then how many electrons can enter into anti-bonding molecular orbital? 1, 2, 3, 4, 5, 6. 6 electrons are enter into anti-bonding molecular orbital. Here asterisk indicates the anti-bonding electrons. As we already know, bond order equals to bonding electrons minus anti-bonding electrons by 2, means 10 minus 6 means 4 by 2 equals to 2. The bond order value of oxygen is 2. The integral bond order value of 2 correspond to the double bond nature of oxygen, and here bonding electrons are more than anti-bonding electrons. It indicates the molecule is stable, and in these oxygen molecular orbitals we see the lone pair of electrons. These pi asterisk 2px and pi asterisk 2py are not completely filled, they are with lone pair electrons, and lone pair of electrons indicates the diamagnetic nature of oxygen. So oxygen is a stable molecule. It has bond order value of oxygen is 2, bond nature of oxygen is double bond, and it is a paramagnetic in nature. In this way we are possible to get some important information about the molecular orbitals, about the molecules from the electronic configuration of molecules. Okay. Let us we go to and let we see energy level diagram for H2 molecule. Here 1s is one atomic orbital and it is another atomic orbital. these atomic orbitals are combining, and here only we see the one electron in the 1s atomic orbital of one hydrogen, and here also we see only one electron in the 1s orbital of another hydrogen. So, these two atomic orbitals are combined, and results in the two electrons in molecular orbital of sigma 1s, and these results there are only bonding electrons for hydrogen. Let we see energy level diagram for oxygen or nitrogen. It is the energy level diagram for nitrogen molecule. Here it is 2s orbital, and it is 2s atomic orbital of one nitrogen, and it is 2s atomic orbital of another nitrogen, and it is 2p orbital of one atomic orbital, it is 2px atomic orbital of one nitrogen, and it is 2p atomic orbital of another nitrogen. These atomic orbitals combine and results in the formation of molecular orbital. In these electrons are enter into the molecular orbitals of nitrogen. Okay. Let we see energy level diagram for oxygen. Oxygen. Oxygen is it is 1s atomic orbital of one hydrogen oxygen, and it is 1s atomic orbital of another oxygen. It is 2s atomic orbital of one oxygen, and it is 2s atomic orbital of another oxygen. It is 2p atomic orbital of one oxygen, and it is 2p atomic orbital of another oxygen. These atomic orbitals are combined and results in the molecular orbital, and these electrons are enter into the increasing order of energy level for molecular orbitals. In this way, we do bond order for molecules, and we are possible to get some important information about the molecules from the electronic configuration of molecules. And also let we see bond order for heteronuclear diatomic molecules. Heteronuclear diatomic molecules, in heteronuclear diatomic molecules, atomic orbitals combine if the electronegativity values are similar. For example, in carbon monoxide, the energy of 2s orbital is lower than the energy of 1s orbital. So, the degree of mixing is too low. Okay. Let us see bond order for heteronuclear diatomic molecule like hydrogen fluoride. Hydrogen fluoride. Hydrogen 1s orbital in hydrogen fluoride, 1s orbital of hydrogen combine with the 2pz orbital of hydrogen, because experimentally that 1s orbital of hydrogen is comparable with the 2pz orbital of fluorine. Here in hydrogen fluoride, HF symmetry allows to mix 1s orbital of hydrogen with the 2s orbital of hydrogen, but the difference in the energy prevents them from combining and overlapping to form atomic orbitals. So, 1s orbital of hydrogen combined with the 2pz orbital of fluorine, and it forms a molecular orbital hydrogen fluoride due to overlapping between due to atomic orbitals are belonging to different elements. The bond order name is heteronuclear diatomic molecules. Okay. Let we see bond order for another heteronuclear diatomic molecule, HCl. Hydrogen chloride. Hydrogen chloride is a diatomic molecule which consists of one hydrogen atom and one chlorine atom. These two atoms are connected by a covalent single bond and results in the formation of molecular orbital hydrogen chloride. The electronegativity value of chlorine is much higher than that of hydrogen. So, the single covalent bond is quite polar in nature. Let me see bond order for another heteronuclear diatomic molecule, carbon monoxide. Here carbon monoxide forms Here carbon monoxide forms triple bond between what is the atomic number of carbon? Yes, the atomic number of carbon is 6. Let me write electronic configuration for atomic number of carbon. 1s2, 2s2, 2p2. The valence electrons are 4 in atomic number of carbon. Then let us write atomic, what is the atomic number of oxygen? The atomic number of oxygen is 8. Okay. Let me write atomic electronic configuration for oxygen. 1s2, 2s2, 2p4. And in this oxygen molecule, the valence electrons are 6. In this carbon molecule, the valence electrons are 4. Here, the carbon monoxide contains 10 valence electrons to form a bond between the two atomic orbitals. Here, carbon monoxide. We also know there are 2 electrons, valence electrons present for carbon electrons in dot like representation, and oxygen has also 2 in dot like representation. They form triple bond by sharing of 6 electrons. Here the 4 electrons are contributed by single oxygen molecule and only 2 electrons are contributed by carbon atom and forms a triple bond to satisfy the octet rule. Okay, let us count valence electrons for carbon and oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Means carbon atom has 8 valence electrons, means it satisfies the octet rule. Then how many valence electrons for oxygen? Let us count. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen also 8 valence electrons. Then oxygen also satisfy octet rule. Then carbon monoxide forming triple bond with 6 shared electrons forms a triple bond to satisfy the octet rule. Means what is octet rule? The tendency of electron to achieve 8 valence electrons in valency shell is called octet rule. Okay. Let me recall what we learned today. The important questions of IP, the possible questions of molecular orbital and IPE point of view is: write the salient features of molecular orbital and draw a energy level diagram for nitrogen and explain the magnetic nature of nitrogen. And another question is: write the energy level diagram for oxygen and write the magnetic nature of oxygen. This is the important point of important questions for IPE point of view. Okay, let us recall our questions, our lesson, what we had learned today. Hello. Okay. First we are learn. We just recall basic concepts of molecular orbital, and then we know some introduction of molecular orbital. That is this molecular orbital theory was proposed in the early 20th century, and this molecular orbital theory has been developed in the years after valence bond theory had been established. The word orbital was introduced by Robert Mulliken in 1932. By 1933, molecular orbital theory was accepted as valid and useful theory, and the first accurate calculation of molecular orbital theory was made by Charles Coulson in 1932. And these are the introduction and the history of molecular orbital. Okay, let us learn salient features of molecular orbital. Let us recall salient features of molecular orbital. The electrons in molecule are present in various molecular orbitals, as the electrons in atom are present in various atomic orbitals. As we already know, we find electrons in orbitals. In case of molecule, we find electrons in molecular orbitals, and in case of atoms, we find electrons in atomic orbitals. The atomic orbitals of comparable energies and proper symmetry combine to form a molecular orbitals. We already learned with an example, only 1s orbital can combine with another 1s orbital, but not with 2s orbital, because the energy of 2s orbital is appreciably higher than that of 1s orbital, and 1s orbital can combine with cannot combine with 2pz orbital because of the different symmetries. So, the atomic orbitals of comparable energies and proper symmetry combine to form a molecular orbital. While the electrons in atom are influenced by one nucleus, as in the molecule it is influenced by two or more nuclei depending upon the number of atomic orbitals combined. Thus, atomic orbital is monocentric and molecular orbital is polycentric. We already know atom contain only one nucleus, whereas molecule contains two or more nuclei, that is depend upon the number of atomic orbitals contained. So, in atom electrons revolve in their orbitals is called atomic orbitals. In atom electrons revolve in atomic orbitals around the nucleus, whereas in molecule the electrons revolve in molecular orbitals around the nuclei. It is depending upon the number of atomic orbitals. Thus, atomic orbital is monocentric because it has only one center, and molecular orbital is polycentric, it has more than one center, and the number of molecular orbital is formed. Hello? 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 Hi Sphero? Hello?
Hi Sphero, this is Nagesh from Bignur.
Okay, what is your doubt Sphero?
Hello?
What is your doubt
Hello?
Sphero? Hello?
Hello, this is Nagesh from Bignur.
Okay, hi Sphero.
What is the difference between bonding molecule and orbital molecule?
Oh, Sphero, right, yes, good question. Bonding molecular orbital has increased electron density, whereas anti-bonding molecular orbital has decreased electron density. It has a node. What is node? Node is where the probability of electron is 0 is called node, and bonding molecular orbital has lower energy. Anti-bonding molecular orbital has higher energy. As we already know, energy is inversely proportional to stability. So, bonding molecular orbital has higher stability, whereas anti-bonding molecular orbital has lower stability. Means bonding molecular orbital has increased electron density between the two nuclei and is of lower energy, and it is of greater stability, whereas anti-bonding molecular orbital has node between the two nuclei and it is of greater stability, greater energy and lower stability. It is the difference between the bonding and anti-bonding molecular orbital. Okay. Okay, let us recall. Bonding molecular orbital has lower energy and anti-bonding molecular orbital has greater energy. The probability distribution of electrons around the nucleus in atom is given by atomic orbital, as the probability distribution of electrons around the group of nuclei in molecule is given by a molecular orbital. We already know in electrons in atom are present in atomic orbitals, electrons in molecule are present in molecular orbital. So, the probability distribution of electrons around the nucleus in atom is given by atomic orbital, whereas the probability distribution of electrons around the nuclei in molecule is given by molecular orbital. And last salient feature of molecular orbital theory is, hello? Hello? Hello?
Hello?
Hi Sphero. May
Hello,
I
I am
know
Ruby Kavyam from Vaira.
please one, what is your
In
doubt
MOE
Sphero?
diagram of, I would like to ask one question.
Okay, what is that question?
In MOE diagram of N2, phi 2py, phi 2pz are below the sigma
Please speak loud.
2px.
Please, can
in
you
what
please
to?
repeat the question again?
And in water that phi 2py, phi 2pz are
Please, can you repeat the question once again?
And in water the phi 2py, phi.
Sphero? Okay. The salient feature of the last salient feature of molecular orbital theory is the probability, whereas okay, let us learn linear combination of atomic orbitals. In linear combination of atomic orbitals, electron has both particle nature and wave nature. So, as we already know, electrons are present in atom, electrons are present in atomic orbitals. So, according to wave mechanics, these atomic orbitals are expressed by wave functions, which represent the amplitude of the electron system. So, it is difficult to all electron systems. Thus, linear combination of atomic orbitals method had been adopted. In general, linear combination of atomic orbitals means combining two atomic orbitals linearly. In these, key points are constructive interference, destructive interference, bonding molecular orbital and anti-bonding molecular orbital. Due to constructive interference, bonding molecular orbital is formed. Due to destructive interference, anti-bonding molecular orbital is formed. As we already know what is bonding and hello.
Yeah. Hello.
Hello. Hi Sphero.
Hello, sir.
May I know your good name please?
Hello.
Hello. Sorry Sphero. Due to constructive interference, bonding molecular orbital is formed. Due to destructive interference, anti-bonding molecular orbital is formed. As we already know what is bonding molecular orbital is and what is anti-bonding molecular orbital, and also constructive interference and destructive interference. Constructive interference means combining two electron waves linearly with same signs in same phase, and it results in the formation of constructive interference. Destructive interference means combining two electron waves with opposite signs in different phases, and this results in the formation of destructive interference. Due to these constructive interference, bonding molecular orbital is formed. Due to destructive interference, anti-bonding molecular orbital is formed. Okay, let us recall types of molecular orbitals. As we already know, there are three types of molecular orbitals: sigma bonding molecular orbital and sigma and pi molecular orbital. Okay. In general, sigma molecular orbital is occurs due to internuclear axis involving nucleus in intermediately. When these two atomic orbitals involves head-on-head overlapping, this results in the formation of sigma molecular orbital. When two atomic orbitals are involving side by side overlapping, this results in the formation of pi molecular orbital. In general, this head-on-head overlapping involves the sigma molecular orbital, and side by side overlapping involves the pi molecular orbital. I would like to say thanks to our secretary sir who provides these marvelous opportunities to us, and I would like to say staff of Magnet Madikonda.